So great effort was required to do this. It took 10 years of serious effort at the Tevatron in order to make this happen. It did happen. Here are a couple examples, slightly enhanced. One event from D0. If you know how to look at this, you'll see that the two towers on the left make a W boson, a little stub up at the top. You say peak quark. This line, the blue line, is a muon. That line is a neutrino that is represented by missing energy. That's another W boson. This stuff down here is another B quark. And that was the signature of a top quark and any top quark being produced. So just a beautiful event in which you can see everything. CDF had their own microvertex detector from early days, and blowing up the vertex there, you can see detached vertices representing two B quarks there, and the other characteristics of this event mark it as a good candidate for a top quark. So that was a big achievement, noticed by the worldwide press, in different languages. Particle physics is over because it's gotten its last secret, something like that. It's never over. So it was beautiful thing that the two collaborations made the discovery at the same time. They made their announcement of the discovery simultaneously. But there was a little rivalry nevertheless. I wrote an article for our journal Physics Today about the top quark, and I sent the graphics editor of the journal a photograph of CDF and a photograph of D0. CDF, which is on the left, you have to admit is more interesting graphically. And so that's what they chose. And when this appeared in the mailboxes, my D0 colleagues came to me and said, how am I going to show this to my mother? So we had to have a special run of other ones made with the D0 detector. Okay, another wonderful aspect of Fermilab. This was started in 1980 as our daycare center, children's center. Here are some of the kids from recent times, cute as buttons, very good. And here's a graduation from kindergarten or preschool or something like that. The children's center has really been a great thing for our employees and also for some of our summer visitors who come with small children. It's wonderful to have high-quality care available. Okay, let's talk about another thing that we've been trying to find. We believe, on the basis of astronomical evidence and now other astrophysical evidence, is almost certain that what we're made of makes up only 20% of the matter of the universe, or maybe 5% of the universe, all told. The other 20% of the matter, very likely, but not certain, because we haven't found it yet, is made up of a bath of particles in which we're swimming, particle dark matter. And if it's true that we're sort of sailing on our planet and in our solar system and in our galaxy through a sea of dark matter, then if you make sensitive enough detectors, you ought to be able to see a dark matter particle bumping into normal matter now and again. We've had a number of efforts at Fermilab trying to do this. Here's the cryogenic dark matter search on the left using electronics semiconductor detectors. Here is a modern incarnation of the bubble chamber being used on the right. Both of these enterprises, as well as everybody else in the world, has set increasingly stringent limits on the properties of dark matter, which is not as satisfying as finding it, but is making progress nonetheless. Neutrinos have been part of the Fermilab program from the beginning. When I talked to Wilson years after he left here, he said that everything was going to be good, but he felt that neutrinos were really going to be the big stuff. A special bubble chamber, 15 feet long, was made to do neutrino physics, because you need a big target to detect these weakly interacting particles. It took pictures like the ones that we saw. Here I have a roll of bubble chamber film. And if you look at it afterwards, roll the leader, you will see on here pictures of events induced by neutrinos and with tracks. that could be interpreted. These early experiments using the 15-foot bubble chamber gave us important information about the nature of the weak interactions, especially a new kind of weak interactions called the neutral current weak interactions that were discovered in 1973 and had to be unraveled. And so we're an important part of the Fermilab program. We're particularly easy to interpret, and for that reason had an advantage over some other techniques. Here's an example of one of those pictures. The reason it has all these tracks in it is that this is a mixture of helium and neon in the bubble chamber, which means that electromagnetic energy, electrons and photons, manifests itself in a jet of particles. It's easy to identify. Other neutrino experiments were done from the very beginning. The first proposal, first approved experiment at Fermilab was called Experiment 1A. It was a neutrino experiment. Others as well. They had a number of purposes. One was to look inside the proton. The neutrino is a very good probe for doing that. The other was to study the nature of the weak interaction in various ways. Here's one of our later experiments called NUTEV. Here's the collaboration. The collaboration was maybe 30 or 40 people at that time. Very large, massive detectors, lots of steel and interleaved with detectors. And one of the classic experiments at Fermilab was to look for a new kind of neutrino called the tau neutrino. This is another one of those particles whose existence we inferred from other experiments. And we could say what its properties would be, but it's still very satisfying to show that it's really there and behaves as expected. So we thought that the tau neutrino, which we figured out how to make in a complicated way, when it interacted with normal targets, could make something called the tau lepton, a very heavy friend of the electron, which itself decays in about a trillionth of a second. And so if you could see nothing coming in, namely the neutrino, an interaction, and then a particle that decayed in the space of a few tenths of a millimeter or a millimeter, you would be able to do that. And a very effective way of doing that was to use photographic emulsion, which has very high spatial resolution. It has the disadvantage that you have to take it out and develop it before you can see what's there. And then you have to know where to look in a very small space in a very big place. And so you want to make a hybrid detector that has the ability to point back to the right place in the photographic emulsion in order to see the events. So these people, the donut experiment for direct observation of new tau, made such a detector which had emulsion targets interleaved with something called scintillating fibers, which I showed you here. They respond very nicely to radiation. And then conventional detectors downstream. And they were able to find a few examples of exactly what was expected. So what you see here is some interaction. Let's look here at the top. An interaction making a few particles, one of which goes a few millimeters actually, and then has a kink in which it's decaying into something plus neutral stuff. And these other three examples also show that. So they demonstrated for the first time that the tau neutrino was not just a figment of our imagination, but was real. And this has now developed a technique that people have used to probe properties of neutrino oscillations, one kind of neutrino changing into others. The next step in accelerator development, both for the good of the Tevatron Collider program and for our future, current and future program of neutrinos, was to replace the main ring. It was primitive by modern standards, and also had the annoying feature that one piece of the main ring actually went through the D0 detector, so it's like having a piece of the accelerator in the liver of your detector. So it was moved to a new place, 1 pi kilometer around, just out the back. Main injector is on the bottom here, and on the top is a novel storage ring made of permanent magnets instead of electromagnets, and so with very low operating costs. Quite a clever innovation. And this has allowed us not only to increase the number of protons and antiprotons that we put into the collider during the days when it was operating, which gave much greater capability to CDF and D0, and also to put unprecedented amounts of proton power onto the targets that make neutrino beams for our current neutrino experiment. So one of the highlights of our current program is to send neutrinos through the Earth. We bend them down by about 3 degrees, send them through the Earth, and they come out at the Sudan mine in northern Minnesota, where 2,400 feet or so underground, there is this magnificent object. The detector is there. It's about 8 meters high. So again, it's massive because neutrinos interact very little, and the flux of them reaching a distant place is small. They are lucky to have this magnificent mural in their mine site. So this experiment has told us a great deal about the properties of neutrino oscillations. We make them here mostly as muon neutrinos. By the time they arrive there, some of them have changed into electron neutrinos or tau neutrinos. And this is really on the leading edge of neutrino physics today to understand these properties. A second newer experiment, also in northern Minnesota, is called the NOVA experiment. Here it is as it's being set up. It's also in operation now. This is on the surface. It's in a building that's as long as a football field, roughly, and you can see that the detector is about 4 stories tall. So these are big detectors in order to register what's happening at the other end. So just a few words about things that we've been doing that don't involve directly terrestrial accelerators. In 1941, Pierre Auger, who was one of the founders of cosmic ray physics, wrote a book translated into English with the title, What are Cosmic Rays? My colleagues are still asking this question, even though we've learned quite a lot in the intervening time. And the contribution of Fermilab and its collaborators to this subject has been to go from sort of cottage industry experiments to really big experiments. The really big experiment we have in mind is one that is actually conducted in Argentina. But if I put the apparatus, the array center it on Fermilab, it looks like this. So it's a considerable installation. There's 1,600 ground stations and 5 stations that look up at the sky. Here you can see a cartoon of a cosmic ray, so a proton or something coming in from way out there, interacting in the top of the atmosphere, making a shower of stuff, lots of electrons and protons and so on, muons that come down to the bottom. Those are detected in the ground stations, but then you can also look up and see the air fluorescing as the burst of energy goes through it. So that's having 2 techniques to look at these things. It's one of the great features in addition to the wide area that they cover in this case. Here is a Google Earth illustration. So you see a few houses over here being illuminated by muons and other things, and then the fluorescence detectors looking up and seeing a piece of track here, a piece of track there, and from that they can reconstruct in 3 dimensions the trace of the cosmic rays and shower that came into their detector. So that's been a very productive experiment. One of the things that they've done is to measure the number of particles that reach us at stupendously high energy. At the energies they're considering, the rate of cosmic rays, primary cosmic rays, is about 1 per square kilometer per year, something like that. That's why you need a big detector and a lot of patience. And what they found is that as you go up above around to the 19 electron volts, a little bit more, flux of cosmic rays abruptly falls off. This was predicted because the universe at large is filled with cosmic microwave background radiation, the famous 3-degree radiation. And if it's really there, we know it's there, and protons of higher energy come along, they will hit the cosmic microwave background radiation and make pions by a process called photoproduction. And so there should be a cutoff at exactly this place in the spectrum. So that almost is a proof of the cutoff is there as expected, but what remains to be shown is that there are actually sources of protons of energies higher than the cutoff would tell them. That's the next step in research. Another intriguing thing that they found is the change in the composition of cosmic rays. As you go up in energy, it looks like they're changing from protons to heavier nuclei. As you go up, that's still work in progress and hasn't been sorted out. Anyway, the industrialization of that kind of research has really led to these results. We've done some astronomical research. So the first is the Sloan Digital Sky Survey, and I'll just show you why it matters to be able to do big things. Here are 500 different supernovae observed in the Sky Survey. These are then followed up for study by the Hubble Space Telescope and other instruments. Here is a couple slices of the sky showing this filamentary structure, stuff out there, galaxies out there, again taken from the Sky Survey. And here is our most recent astronomical enterprise, the Dark Energy Survey, Chile. Here just one little illustration of what they've been doing. They and their colleagues have discovered some things called dwarf galaxies, which are satellites of our own galaxy, but are much smaller and darker. As we knew about before, an illustration that our senses are limited, our instruments are limited. When we make improvements in our instruments, we discover new things. Here, by a technique using spectroscopic information, they're able to get rid of the foreground and to see the dwarf galaxies on the side. Okay. So, two last things to talk about. One is our participation in the Large Hadron Collider at CERN. There are two elements of this. One is to build pieces of the accelerator, in particular the magnets that bring the beams into small spots and give high collision rates. So a number of those are fabricated here at Fermilab by my colleagues. They look like big things, but they take a lot of meticulous work. The LHC, the Large Hadron Collider at CERN, is bigger than our machine. It's 27 kilometers around, or 17 miles around. The CERN laboratory is this little triangle. That's the LHC. It's about 100 meters underground. I always tell my people, my friends from CERN, you know, they've got this nice little airport, and we've got a much bigger airport. They've got this cute little lake, and we've got a much bigger lake. They have the Alps. Anyway, there are two main experiments, and Fermilab is the United States headquarters for this CMS experiment, which is over here. Their friendly rival, the Atlas experiment, is here. And in this accelerator, which has about 7 times the energy of what our Tevatron had in its heyday, protons and protons collide head-on, and people have done great work. Including, so here's the CMS detector that my colleagues participated in. Big and brawny, 5 stories high. Lots of steel, perfectly fine electronics that you see here. The trackers, cells, diameter. And these people, as you will recall, on July 2012, together with their colleagues at the Atlas experiment, discovered the Higgs boson, new insights into the nature of the origin of mass, the way that we can respond, and so on. And they're now happening with a new run of the accelerator, some higher energy, 13 TeV. Just today, our CMS colleagues are switching out some of their central tracking apparatus for improved apparatus, and we expect more great things from the future. Okay, what's happening at Fermilab now in the future? We're moving on with a suite of experiments. This is from the micromoon experiment, one of their first neutrino events, in a new kind of detector for us to use for neutrino research. It's called the liquid argon time projection chamber. It serves as a prototype for what we hope will be the new experiments that we'll do in the future. And they're off to a running start. This gives pictures of bubble chamber aspect of much finer quality, telling you about the characteristic of the particles that are emitted and allowing you to say things quickly, electronically, and in great detail. So that is off to a great start. We're building muon experiments just behind us here. On the left, just behind the booster, you see the muon magnetic moment building that's completed, and I'll show you something inside it. And then some old pictures from last year. The building being completed next to it is for a new experiment. Extremely rare, we think. Disintegration of a muon into an electron transformation. Here is the magnetic ring for the U.S. magnetic orbit experiment. This was a few months ago. They've got working getting ready for data taking. And maybe by the end of this year, beginning of next year, they will begin taking data and give us answers. After that, the big deal that Fermilab has involved is to send neutrinos not just 500 miles to North Minnesota through the Earth, but 800 miles to South Dakota, plus 100 feet South Dakota, where there will be very large underground sectors to elaborate the mysteries of neutrino oscillations and other aspects of neutrino physics. So when I came here to Fermilab for the first time, so the university was a great place for the future. When I came here, it was the most exciting place I could imagine being. And I wondered that it would be made for other young people the most exciting place to be. My colleague John Peoples, when he was director, liked to say that at Fermilab we make things and they work. And if you look at these pictures, I would amend his statement to say that our colleagues make very beautiful things, and they work. Thank you very much. Some people